Hello everyone. I'm going to talk about the next section of the chapter 5. So in the previous class we have talked about three different cases where the lens is actually doing the Fourier transform. So we have studied one case where the input was placed before the lens and against the lens. And today we are going to talk about this case where the input is placed in front of the lens with the distance d. Okay, so we have a input and then we have a Fresnel diffraction, and then we have a lens, then we have a focusing. So it is quite different from the case A. So let's see what we can do. So before we do it, we are going to talk about two different Fourier transforms. One is the F0 is the Fourier transformation of the input transparency. Actually, the image, you can say that. So F0 is ATA, the amplitude and the transmittance of the input transparency, and its Fourier transformation. Fi is the input light field. Okay, Fi, the Fourier spectrum of the light incident on the lens. Okay, Fi. So in this case, after this, you get a certain Fourier transformation. At this point, incident light has a Fi incident. Okay. So assuming the Fresnel or partial approximation once again, for the propagation of the distance d, then using equation 4-21, we're going to talk about later on. But anyhow, there's an incident Fourier component of the light is actually the Fourier component of transparency times this is the propagators actually. So it is we need to go back to the angular spectrum method to understand this one. So I'm just adding this one, the Fresnel approximation and the angular spectrum. So if you go back to chapter 4, you will find these slides 4.2.3. And here we have concerned about the transfer function of a propagating through the free space. So if we have any light and if it is going to propagate, then it has these transfer functions h fxy is given by this one. So as long as this Fourier component is satisfying this condition, it has this factor, okay? And then as a result of it, if you do the Fourier integral a little bit carefully, then you can see that it is e to the kz times this one. Okay. So in previous case, we have propagation of the light through this input over the distance d. Okay, so we have to put the d over here and d over there. Okay, but the e to the ikd is kind of a constant, so we dropped it. Okay, we dropped it. So we have a transparency, and then it is propagating through the d. Then you get this expression for the incoming lights Fourier transformation just before the lens. And then our field at the focal point F is given by this quadratic face with the pulpit function, and this is our familiar Fourier transform factor. And then assuming that the pulpit function is 1, remember that Fourier function is 1 means we are using paraxial approximation, which means light is very confined to the center of the lens. So that it does not see this size of the lens, so that it is going to be passing through near the center. Okay. So in this special case, when we have a p equal to 1, then you get the ui times this factor is actually this is 1, and then we have this exponential term, and this is nothing but Fourier transform. Okay, and then it is given by this phase term times fi. Okay, and then by definition fi times this factor propagation over d, and then we have a d term here, f0 times d term, right? Fi is this times exponential term, and then it is actually given by a certain phase term times Fourier transformation of transmittance function. Okay, Fourier transformation of this transformation. So this is Fourier transformation of TA. Okay, so what it means is that there's a phase term, and then note that there's a d over f term here. So if d equal to f, then this is 1, and then the whole term goes away, and then it is just the Fourier transformation of the transmittance function. Okay. So if d equal to f, then we get uf is nothing but Fourier transformation of TA. Okay, this is the TA. Okay. This is also Fourier transformation of TA. So, so we have two cases which is identical, but note that d equal to f, and then we have the exact same thing. But if it's not equal to f, then we have some certain phase term. This term. Okay. This term is going to survive, right? But if you take the absolute magnitude, it doesn't matter, right? So quadratic phase factor again proceeds the transform integral, but it vanishes for the very special case d equal to f. Okay. So here we have entirely neglected the finite extent of the lens aperture. That means p equal to Fourier function is going to be 1. This is our big assumption, or we can say that this is a paraxial approximations. Okay. So we have to think about some special case. If this lens extent is comparable or sometimes smaller than the object, okay, the screen, then what's going to happen? And this is the case. So do you have an initial aperture? This is the input plane, and then the light is coming in this way, okay, and the lens is there, and then we have this focal plane here. Okay, so in previous case, this aperture was much smaller than the lens, but it is of about comparable size. So that because of this factor, right now what we are going to do is depending on where the light is going to illuminate. We have some portion, which is shaded region, is going to be passed through the lens, but the other region like this, here and there, is not going to be transformed. So we have our only portion that is going to be Fourier transformed here. So that is called vignetting. Vignetting means is that we have a certain leftover here. Okay. So this is the vignetting. So basically, so in this case, vignetting is actually given by this function. This is the pulpit function. So in this case, we cannot say that p equal to 1, but it has a certain function. But note that it has a certain shift here. It is given by this relationship. So assuming it has a distance d away from it, and then we have a f, and then we have a certain magnification factor d over f, and then we have a new coordinate like this, and then we get this shift. So basically it is going to be shifted over here. Center is there. Okay. Like this one. So this object center is there, and then we get the pulpit functions, and then we get the Fourier transform. Only the part of the transmittance function is going to be Fourier transformed. Okay, this is the how we correct the finite lens size. The limitation of the effective input by the finite lens aperture is known as a vignetting effect. For a simple Fourier transform system, vignetting of an input space is minimized when the input is placed close to the lens and when the lens aperture is much larger than the input transparency. So that means, previous case, vignetting can be minimized in this case. So the input is just placed against the lens. But in practice, it is often preferred to place the input directly against the lens in order to minimize the vignetting, just like we have seen before, right? And then, now we are going to talk about input placed behind the lens. Behind the lens, that means we are going to talk about the third case here. So the light is coming this way, and then it passes through the lens, and then our input is behind the lens. So within this focused beam, the input is placed here. So from the focal point, we have a distance d. Okay. Let's see how it is going to change. So we are going to consider a figure 5.C, the third problem. The input is now located a distance in front of your focal plane of the lens. And in the geometrical optics approximation, the amplitude of the spherical wave impinging on the object is A times f over d. Okay, so that we get the reduction of the amplitude like this. And then the particular region of the input that is illuminated is determined by the intersection. Remember that intersection of the converging cone of the rays with the input plane, right? So we have this is the cone, converging cone, and then we have this is input plane. So we have only this portion. Okay, this is the intersection of the converging cone of the rays with the input plane. If the lens is circular and the diameter I, then circular region of the diameter is L times d over f. Okay, so that it is by the geometrical optics, it is reduced by factor over this one. Okay, and then the effective region can be described with a Fourier function given by this one, so that it has a certain magnitude is given here. Okay, so we have a distance d from the focal point. From here to here is f. Okay, and using the partial approximation to spherical wave that illuminates the input, the amplitude of the wave transmitted by the input is going to be this one, transmittance, and then it has a propagation. This is the cone reduction, and then this is the pupil function, and then this is the distance d, which is propagation, free space propagation, and then we have this transmittance. Okay, and then utilizing this as our input field, yeah, and then we just use the Fresnel equations, and then we end up with this factor here. So once again, note that the quadratic phase factor, the focal plane amplitude distribution, the Fourier transformation of that portion of the input sustained by the projected lens aperture. The quadratic phase has been disappeared because of this factor. Okay, this is a free space propagation, and this is the minus q square plus eta square, and then there used to be plus q square plus eta square, and it is cancelled out. So that once again we get this is going to be Fourier transformed, so that we have a Fourier function times our transmittance. So that in comparison to previous case, we have a certain factor is added up, okay, for Fourier transformation. Okay. As d increases, larger transform size. As d decreases, smaller transform size. So depending upon these Fourier functions. So example of optical Fourier transformation is this. So if you have this is our aperture, then if you do the experiment using the lens, you get this Fourier transform spectrum. Okay. Now we are going to talk about image formation, the monochromatic illuminations, and we are going to talk about image formations and then impulse response of a positive lens, and then we are going to discuss this is the transmittance, and then it passes through here, and then pass through the lens, and then it is eventually transmitted to here, so that this is the object and image. So you have done this before, a long time ago, when you were high school or freshman. Then you get this one, and then depending upon this object, image, something like this. So this is the geometrical optics, and this is our Fourier optics. So we are going to describe how we can discuss the wave, in terms of a wave, how this object, so object here is a certain aperture, is going to be projected into image. Okay, so that's the thing we are going to do. And we are going to talk about it in the next video. Thank you for listening.